before we talk about this other way of simplifying Boolean logic circuits, we're going to introduce some terminology. We have a Boolean variable. So in the previous example, the x and the y and the z would be the variables. So this is a variable whose only possible values are 0 over 1. Remember, we're thinking of it in terms of false or true. A literal is the word we're going to use to talk about a Boolean variable or its complement. So when you think about we had x, y, z bar plus x, y bar, z bar plus x, z, the literals that we have are x, y, y bar, z, and z bar. Those are the literals that you find in this particular expression here. So it's a variable or its complement, a variable or its negation. And then a min term is a Boolean product of literals. In other words, each of these here is an example of a min term. And there's lots of different ways to write min terms. It depends how many variables you have and which ones are negated, which ones are not. So a little bit of more terminology we're going to need that will be helpful for you to know is notice the way our example was written. It was x, y, z bar plus x, y bar, z bar plus x, z. Notice that each term is a product. So these are each Boolean products, and then they're being summed together. They're being added. So a Boolean sum of Boolean products is exactly what we have here. And again, since each of these terms, we call them min terms in this context, you can think of a Boolean sum of Boolean products as just a bunch of min terms added together. You can also call this the sum of products expansion. And yet another way of talking about it, which you might see in other contexts, is DNF, or disjunctive normal form. So our big question was, how do we make our Boolean logic circuit simpler and still give us the same output? In other words, the thing to think about is this logic circuit we had is going to have the same output as just the variable x by itself. If we made a complicated truth table for this logic circuit, we would get the same output as if we just considered the variable x by itself. So what we're looking for, to make it more explicit, is we're looking for a minimal expansion of our Boolean expression. And Boolean expressions, sometimes we call them Boolean functions. So those are just some phrases to look out for. And what do we mean by minimal? Well, we want the fewest min terms. Remember, min terms are those terms that appear in the expression. And we want each min term to have the fewest literals possible. So think about our example again. We went from having x, y, z bar plus x, y bar, z bar plus x, z. We had 3 min terms, each with either 2 or 3 literals. And from there, we went to just having x, which is 1 min term and 1 literal. which is a pretty good reduction. I mean, that's about as good as we can get. So this is the goal of what we're trying to do. We want to have the fewest minterms, and each minterm has the fewest literals possible. Of course, we want the same truth table output. That's important as well. And the technique we're going to talk about here is called Karnaugh maps or K-maps. Let's take this example here of a Boolean expression we want to simplify using K-maps. And this will be our way of seeing how K-maps operate, and we'll in a moment look at the general principle behind how you use the K-map. So in order to make a K-map, what I need to do, since this is a 3-variable K-map, I'm going to make a 2x4 table, and I'll make the rows be the possibilities for x. So x or x bar. And then the columns will be every possible way of having y and z being negated or not negated. So we'll start with yz, and then next we'll do yz bar. Now, this might not seem important now, but you should notice that when I went from one column to the next, I only changed one of my literals. So the z became a z bar, but the y stayed the same. That's going to be important for us to be able to use the Boolean algebra properties in the background to simplify our expression. So following that principle of only changing one literal at a time, when I write my next column heading, I can only change one literal here. So if I change the z bar to a z, well, I'm gonna get something I already have, so that's not helpful. Instead, what I'll do is I'll change the y to a y bar and keep the z bar as a z bar. Okay, so again, you want to just change one literal at a time. And so finally, the last possibility we have is y bar z. Okay, now how do we use that setup to record what we have here? Well, let's see, we have x, which is the top row, yz bar. Yz bar is this column, so that means we'll put a 1 here. Or you could shade it in or put a check mark or something like that, but we're just going to put 1s there. Next is x y bar z bar, so that's the x row and the y bar z bar column, so put a 1 there. And then we have x bar yz, so now we're in the second row, and then the yz column is the first column, which gives us a 1 here. And then finally x bar y bar z bar, which means we're in the second row and the third column. All right. So now what I'm going to do is figure out ways I can simplify my expression. So the thing to notice, for example, in this cluster of ones that are right next to each other horizontally, what does this mean? It means that everything is the same except y and y bar. In other words, it's like taking these first two terms and factoring out the common factors of x and z bar, and then having a y plus y bar being all that remains. And as we saw earlier in our example, when you have something of the form y plus y bar in Boolean algebra, that'll give you just a 1. And so I will circle that cluster of 1s. And that will help me reduce at least that much of it. Okay, and so I'm going to look for other clusters of ones like this. I notice that I have a vertical one here. What does this vertical one mean? So this vertical cluster of ones in a 2x1 formation here, what does that mean? It means that we have y bar, z bar, but it's either x or not x. So that x or not x part is just going to become a 1, which will make us have simpler terms. And this one here is just by itself. It's not horizontally or vertically adjacent to any other ones, so we just leave it alone. Okay, so reading this, what do we get? So our simplified answer here using these Boolean algebra principles in the background that we just talked about, this green cluster of ones, this green rectangle of ones is going to be just x z bar, because we have y or not y in there. That just becomes 1, so all we have left is x z bar. And then we have the pink, which is x or not x, so that means we don't care about a literal of that has x or not x in it, so that means we just have y bar z bar as our pink term. And then we just have this term left over by itself, the x bar y z. So we just copy that in, and there's nothing more we can do there. And sometimes this is as much as you can simplify. We had 4 terms, 4 min terms, with each term having 3 literals, and then we reduced it to 3 min terms, 2 of which had 2 literals instead of 3 literals. So there's definitely some improvement there. Not as much as with that first example that we were able to do by hand, but definitely some significant improvement.